So, this is third lecture of third week. Now we will be seeing some fundamentals. Again, it is all to support probabilistic risk assessment because you should be able to perform in a justified way, I mean as a trained person, the probabilistic risk assessment. And as far as statistics is concerned, you can see it shares a good amount of space with even AI and artificial intelligence and machine learning algorithm. So, it is very important. So, in this lecture we will take statistics and probability in relation to PRA, and I would add even machine learning algorithm. So, let us see fault tree development, logical operators. We have seen fault tree I think reasonably, of course in a quantified manner only. Then fault tree, what are the guidelines, Boolean laws. Boolean laws is very critical to analyzing the fault tree. Let me make it very clear. If it is a small fault tree or event tree, we can manually do Boolean logic analysis and get the results. But when system becomes very complex, computerized model are to be used, and most of the computer model, they have this facility for Boolean processing of events. So that we can come to the reduced fault tree or reduced event tree. Okay. Events are not repeating in various branches of the fault tree in a simple way actually. Probability distribution, which is very important, cut set evaluation, you know cut set. Every component is an individual in this thing, but when two components together they meet, they lead to the top event for fault tree, it is called cut set. So, that means if these two events fail together, they will lead in simple language. So, they are called cut set, and common cause failure is an important thing. So, we will be discussing it all through. So, we discussed the fault tree and we saw only top event over here, and then so like ECCS or power supply failure. So, fault tree starts from top, so top event, and it is a rectangular thing. Then we have a line, the interconnection which are there between two events. So, we have also seen use of OR gate. So, if event A and B, sorry, the B should be here. So, if A and B are there, they will be plus through OR gate. In AND gates, it represents redundancy. So, it gets multiplied actually, So, it is called AND gate. And then we have input to logic gate. This is a basic event we call. If a component is there and we do not want to, like a diesel generator, if we do not want to model it further, if we want to represent it, though diesel generator has many subcomponents, but if we want to, so we'll indicate diesel generator as a basic event. But if we do not want to stop at DC, we want to analyze it as a fuel oil system, lube oil system, then control system, then those wherever you stop, it becomes the basic event. If you are stopping and there is not, it is you are not, you want to analyze it further, you will indicate it that way. Okay. But basic event means the fault tree terminates there actually. Okay. And then intermediate event, in between event, like independent event we saw in previous fault tree, it is an intermediate event. So, a fault tree will have many intermediate event which will be connecting to the basic event to the top. Transfer gates. If we want to transfer certain operation from one node to another node, the transfer gates are used, and transfer in gate and transfer out gate. So, if some information is coming from some other gate, it will be. So, this is where you do not want to draw in simple word, you do not want to repeat the fault tree, but you want to take input of some branch of the fault tree and connect it here. So, these are basic operators one should know when we talk about the fault tree. Yeah, I was talking about this event. In fault tree, I am not sure whether it is a basic event. So, I will call undeveloped event. Okay, I will stop there. That means the next other persons, they will know we have not gone into the detail, and here if required we can further develop it as and when required. Then house event. The house event is one event where we want to switch to the enable the on and off. Suppose if there is a fault tree and this is house event, in a particular simulation we want to remove this event, remove that branch. So we will use a house event, we will keep it off, we will switch it on. So that means it helps in simulation of the fault tree, exclusive OR gate. So it is nothing but OR gate, but it has got one special component which change the logic operation. So logic operation results in output only if one of the input occurs. So this input, unless until this input occurs, identified input, the output of the fault tree will not occur. This is the exclusive OR gate. Now we have a name of the priority AND gate. They have priority. If they do not come in some sequence, then it will not be, output will not occur. It has to be in some sequence, like pump, then breaker, and this one is another breaker. So if I have decided some sequence, it has to happen in that sequence only, then only it will be counted. If this is inhabit gate, the output occurs if the conditional event is satisfied to one event, which is a event, conditional event. If unless until that event is satisfied, the output will not occur. Okay. So these are the important gates in the fault tree. And then let us learn some fundamentals, because we have to see Venn diagram. So the exclusive event, independent event A and B. So event A and B, they are independent, So this particular Venn diagram is representing their independency. Interaction of independent event, it is represented like this, that is overlapping factor. So A plus B is A union B, plus is treated as union. So it is OR gate, but actually if they are overlap, probability of A union B is equal to probability of A, probability of B minus probability of A interaction B. The interacting overlapping area should be removed. Okay. Now we have this intersection of event A and B. Okay. A B is so it can be written as A interaction and B, that is AND gate is there, and A and B, and then here A interaction B can be represented as probability of A multiplied by probability of B. And this interaction area is written as AB overlapping area. It can be shown here in AND gate. So this area will be relevant. And now Boolean law. There are 9 Boolean algorithms that are there. So this is one is commutative. That means AB is equal to BA. If we change their place, it doesn't matter. A plus B is equal to B plus A. So they are called commutative law. Associative law is A bracket BC, then it can be AB bracket and then C. Okay. A plus BC, AB plus C. So they are called, which association is happening with other association, it doesn't matter, and that's how. Then idempotent law, the A into A is equal to A plus A is equal to. This is the heart of our Boolean reduction. If same event is representing in two places in AND gate, then it is A. If it is represented two events by OR gate, then again it is A. So repetition of event doesn't get reflected twice or the way it is actually. Absorption law, A multiplied AB plus C. So if since this is supreme here, A plus A, so it is A, and A plus AB is equal to also A, because A is there in both the places. So this is called absorption law. Distributive law is A bracket B plus C, okay, is equal to AB plus AC. So this can be there because there are third element here. Here the A was multiplied by A, so that was there. Distributive law is here, AB and bracket AC. So A multiply you get, and then you get a BC. So complementary law, A and complement of A is equal to null gate, okay, and A plus A is equal to complement A plus A also is again null gate, okay. Then De Morgan's theorem, if complement of AB is a complement of AB in multiplication mode also, and complement of AB multiplication mode is also can be written as complement of A plus complement of B. So, yeah, I think there are 7 and others law you can go through the books and all, but these are very important 7 laws that we are discussing over here. And now, when we look at the fault tree, you see the Boolean logic is used here for understanding the fault tree. Let us say we have this fault tree safety injection system. Okay, its a failure probability is this much. So, independent event, pump and valve are there. Then P1, P2 pump systems are there and valve systems are there. So, I have got an AND gate here. So, P1, P2 will be a AND gate and valve V1, V2 are there. So, system unavailability is equal to common cause failure. You can say independent V1 plus V2 over here, and then P1 into P2 because they are through AND gate and this was through OR gate. So, this is how the first order cut set here is common cause failure and the valve V1 and V2. So, if this thing fails, they will take system to the failure status, and if P1, P2 fail independently, it will not affect the system because they are representing redundancy. So, they together have to fail the second order cut set. So, P1 and P2 only will take you to the top. Okay. So, this is how the fault tree is there that we have indicated here. So, order of cut set and all this they can. So, this description, background description you can see over here, and then fault tree analysis, significance of common cause failure. Okay. So, you can see the top fault tree we can make by AB plus AB and C into D because here AND gate is there. So, A plus B comes from this branch and C into D, and then multiply ACD and BCD. Failure probability of power supply system is 4.2 10 to the power minus 4 because quantification we have not shown here. It was to give the importance of the diesel generator over here A into B. So, we have diesel generator failure probability, let us say 4 into 10 to the power minus 3 here. If that is failure probability over here, then T is top event. It will be comprised of this one plus this one and multiplied by this into this top event, you know. So, we have this top event probability and this comes to 3.87 into 10 to the power minus 8 per demand. Okay. Now, if common cause contribution is considered as 10%, then T into 10 to the power 3.87, that is and point this one. So, these two together they will make it 4 because from here it is less, but if it is this quantity is coming in, so common cause become dominating factor. So, 4 into 10 to the power minus 4 that is the. So, here it is trying to emphasize in this slide what is the importance of common cause failure. If we do not take common cause failure, what are the view will get over optimism while giving the by considering only independent failure actually. So, now again if I want to understand in detail what is common cause failure. So, common cause failure is characterized by common cause failure attributes. If there are, like we saw, two components diesel generator were there earlier, and now we have component A, component B, component C. They are part of a redundant configuration. That means all the three are doing the same job. So, even if one component is there, it is sufficient for us, it will meet the purpose. But what common cause does is, it kicks off all the component, it knocks off all the component, and that the common cause component could be anything. Okay. So, what are the attributes? Coupling mechanism. There should be some coupling mechanism. This coupling mechanism could be increase in humidity, it could be flood water that has come to that level, it has failed all the breakers. It could be some same oil was added, contaminated oil was added to all the three. So, that became a and then root cause. Root cause is contaminated oil, okay, or flooding level or seismic level. So, an instantaneous failure. Common cause failures is characterized when the all redundant components they get knocked off. Then only importance of, if one component is failing at one point, then there is a time gap between second and time gap between third, then it may not form part of the common cause failure. And if I see the mathematics is this, probability of A intersection probability of B is equal to, it is written like this. But actually probability of A into probability of B, that is not correct. That is not correct. We have to show the dependency. For dependent events, the expression can be written as probability of A into probability of B is equal to probability of A into probability of B given A. It is a conditional event, you know. So, that is where this factor is coming in, and probability, it can be written otherwise also. Probability of A interaction probability of B is equal to probability of A into probability of A given B. Okay. And that is how there are many models and methods that are available, but this slide tells you, gives you a sense of quantification of common cause failure. Why we are working more on common cause failure is because it is significant. It can knock off a system or disable a system in part if partly if the same event is knocking off all the system. And then there are different model pass. So this is the most used model, beta factor model it is called. So beta, it is a ratio of I am using U. It could be failure rate also, it could be anything, but I am using U means unavailability. Unavailability of common cause failure divided by total unavailability. So UCC failure, common cause failure unavailability in a system, you have to collect the data and get, say, how many times it has failed on common cause failure, you got U, and how many again UCC plus independent failure of the system. So UCC plus independent failure, it gives you UCC plus divided by UT. So this makes a total statement. This is the expression over here, and I would say just for the getting a feel of it, even if you study a common cause failure, this model, it is sufficient for this scope of this course. Then further, if you want to go into detail, multiple Greek letter model where we have this unavailability of the nth order, it takes into order 1, 2, 3. So at 1 between 2 up to 2, the sensitivity is very high, but as you go tier 2 and 3, the data changes. And total availability, M is group size, what are number of component there in the group and number of component which makes the system unavailable. So like that, and then you have here. Then alpha factor model. In fact, after beta factor model is alpha factor model which is used. This is a 4 parameter model, gives as alpha 1, alpha 2, alpha 3, alpha 4. See, importance of the various alphas it is given. This model is also used in fault-free modeling when it is required to estimate availability from common CCFG, okay, having order 2n, common cause factors having group, common cause factor groups which are having order 2, 3, 4. Okay. So I would say, since you have to get a sense of the system, probably our scope will cover only common cause failure using the beta factor model. If you are interested, you can see, for the sake of completeness or this thing, you can see this thing. But to me, it is more important that we understand in prognostics and health management detection of common cause failure, because it can. So we should develop different sensors, like plant humidity has gone above, and we know that it can knock off the, it is a source of common cause. So we should have a sensor in the plant which tells us the humidity has gone from 50% to 80%, or we should know that the water level rise can affect all the breakers in the system because of shorting. So we should have a common cause factor. So beyond empirical, if we go into physics of failure method, that is much more insightful and gainful. Instead of going into numerical. Numerical is good, it does not require much effort, only modeling effort. But in real time, we should determine what are the defenses that are available in the plant and how far the common cause possibility still remains there, and develop a prognostics and health management program for those levels actually. So we saw probabilistic, Boolean law, fault-free cut sets. You would have understood fault-free quantification and significance of common cause failure. So I would think that common cause it would have been understood by many people, and now they must be knowing how to develop a qualitative fault tree, quantitative fault tree, and if you have done that, and if you know how to analyze the data also, Boolean logic reduction, probably you now know what is PRA, which is the mainstay for our system approach in PHM model.